Hi Wildcats. This is a couple of example problems from Unit 1, Focus Question 2. So in this we're going to be looking at objects that we know are in simple harmonic motion, both a mass spring system and then a pendulum, and we're going to try to determine the different variables associated with a given system. So in our first problem it says a mass spring system. It has a period of 0.9 seconds. So let's write down what we know. 0.9 seconds is the period. If the mass in the system is 1.4 kilograms, all right, so they told us mass, 1.4 kilograms. What is the spring constant of the spring in the system? So spring constant is what is unknown here. So this is what we're given, this is what we're known. Let's see, we can draw a quick spring system. So here is my mass hanging from this spring. We know that this is 1.4 kilograms, and we know the time it takes to go from, this is, we'll assume it's at equilibrium already, so the time that it takes to go down, back up, and then back to equilibrium, that would be its period, and its period is 0.9 seconds. So it goes through one full cycle in 0.9 seconds. Okay, so what is the spring constant? Well, if we look at our equation sheet, or we just remember that we have an equation associated with mass spring systems, but that equation tells us its period. So the period of a mass spring system is equal to 2 pi times the square root of the mass in the system divided by the spring constant. So if this is the equation, let's see, does it have the variable we're looking for? Does it have spring constant? Okay, yes it does. Does it have mass? Yes it does. Does it have period? Yes. Do I have only one unknown variable in the system? Yes, it's spring constant. So I can use this equation, right? Because I have period and I have mass. So now this has just become an algebra problem. Like all the physics is done. Because we've figured out the right equation to use and that we have the variables associated with this equation. So from a physics problem solving standpoint, we are already done. Now it just becomes a math problem. So let's use our algebra skills. I need to solve for k. So I need to get k all by itself on one side of the equation. That's my unknown. So very first algebra step I'm going to do is divide both sides by 2 pi. Okay, so that's gone. So now I have t over 2 pi is equal to the square root of m over k. All right, so how do I get rid of a square root? Well, in order to cancel out this square root, the opposite is to square, right? The opposite operation. So I need to square both sides. So squaring this gets rid of that. So you can distribute or not if you want to. I'm going to, just so that I have one less thing to keep track of. T squared over the squared 2 squared, so that's 4 pi squared. Okay, so now I'm at t squared over 4 pi squared is equal to m over k. So I need k, it's on the bottom. Gosh, we hate problems where the variable is unknown is on the bottom because it makes us do, there's a number of ways to do this, but it means more algebra. Okay, so let's multiply both sides by k is how I'm going to do this, although it's not the only way. I think it's the uses the simplest methods. So now I'm left with k times t squared over 4 pi squared is equal to m. Well, if I was solving for m, I could just plug in the numbers, but I'm not. I'm solving for k, and it's not by itself. So I need to get 2 pi squared over 4 pi squared away from this side and over here. So I need to take the opposite of it. So 4 pi squared over t squared, right? Because now 4 pi squared up top and bottom cancel, t squared canceled. If I do it to one side, I have to do it to the other. So then 4 pi squared over t squared. So now those cancel and this cancels. So the only thing I have left on this side is k. So k is equal to mass times 4 pi squared over t squared. Yay, I have k all by itself. Okay, so now I can plug in numbers. Mass is 1.4 kilograms times 4 pi squared. Now, I don't think we write this, but when you put this in your calculator, make sure you're putting pi squared in parentheses because this to get the square, not to square everything, but just the pi. Okay, all divided by t, which is 0.9 seconds squared. Okay, so if I put this into my calculator, I get a big long number, but to me, to 3 sig figs, I get 68.2. So my answer is 68.2. So now we have to just stop and think for a second. I like to encourage you to think about what units we have. So only units I have left are kilograms over seconds squared. Okay, so if you wrote this, you'd be good. Some of you, though, might be thinking, Mr. Weber, in my notes, it says that the unit for spring constant is newtons over meters, and that's not what I have. I have kilograms over seconds squared. Okay, you are correct, but these two are the same thing. I'll show you why. Newtons over meter squared, if you remember from focus question 1, we talked about a newton is a kilogram times a meter over second squared, meters per second squared. Okay, and then we have that over meters. So this meter is also on the bottom. So I'm left with kilograms times meters over meters times second squared. That's what newtons per meter works out to be. And if I look at that, my meters are going to cancel. So the only units I have left are kilograms over second squared, which is exactly what I want. Or excuse me, that's exactly what I got. So that's good. It tells me I got the right unit. On your answer on a test, quiz, homework, whatever, if you left it at kilograms over second squares, you are correct, because that's what newtons per meters simplifies down to. Or you could write 68.2 newtons over meters. Either or, these are the same thing, so you could write either or. Okay, so 68.2 newtons per meter is what I end up with here for my answer. So that's a mass spring system. Let's look at a pendulum system now. In this case, a student is building a clock, because who hasn't built a clock, with a pendulum. Oh yes, we have all built grandfather clocks. In order for the clock to keep proper time, it needs to have a frequency. Okay, they're telling me things. Frequency equal to 0.714 hertz. Okay, what length should the student design the pendulum be for the clock? All right, so we are looking for the length of the pendulum. So here is my pendulum right here, and its frequency, so in 1 second, right? Hertz is 1 over seconds. It has a frequency of 0.714. What they want to know is, in order to have that frequency, how long do I make the string, or however I'm building this pendulum. Oops, no naked numbers. Okay, hertz, 0.714 hertz. So what is the length? Well, again, we look at our equation sheet or think about it. We know we have an equation for period of a pendulum. Period and frequency are related. Okay, that's a good start. It is period of a pendulum is equal to 2 pi times the square root of the length of the pendulum times the acceleration due to gravity where the pendulum is. So whatever planet it's on, we're going to assume that this student is on Earth because we haven't been told otherwise. Okay, so let's see. Will this equation work? Well, it has length, so that's good. Acceleration due to gravity, I told you, and we have written down, is always, until we learn otherwise, 9.81 meters per second squared. Okay, so this is just a constant that we have, and it is on your equation sheet. So we have this. Length is what we're looking for, so that's good. But period, I don't have period. Unsolvable problem? I know what you're saying. You're saying, no, it's not, Mr. Weber, because frequency and period are related. So if they tell me the frequency is equal to 1 over period, or period is equal to 1 over frequency. So if they tell me frequency, I can get period. It just means I have to take 1 over the frequency they give me, which in this case is 0.714 hertz, or 1 over seconds, right? I could write this as 1 over seconds. So there's my seconds that I should get, because the unit for period is seconds. So 1 divided by 0.714, I get a period of 1.40 seconds. Okay, so now I have period, 2 pi is given. Length is what I'm looking for. Acceleration due to gravity is a constant that I'm told. So I can solve as soon as again, physics is done. Physics is done. We have now just an algebra problem to do. So same as before, we need to algebraically rearrange this. I'm going to start by dividing both sides by 2 pi. So gone, gone. Pi over, or excuse me, t over 2 pi is equal to the square root of L over a sub g, or acceleration due to gravity. I need to get rid of this, so I'm going to square both sides. So t squared over 4 pi squared is equal to L over a sub g. Look, L is on the top of our fraction this time, so I don't have to do a whole bunch of extra work. I can just multiply both sides by a sub g over 1. A sub g over 1, so that's gone. And so I'm left with the length of a pendulum is equal to its period squared times the acceleration due to gravity divided by 4 pi squared. All right, so time or period is, we solved, it is 1.40 seconds. I need to square that. Acceleration due to gravity is 9.81 meters over second squared, all divided by 4 pi squared. So if you put that into your calculator, you can pause and do that if you want. I've done that in advance, so I get a length of 0.487. Now let's check our units here. Okay, so length, we know it should be meters. So the question is, a way for us to check our answer is, did we get meters? Well, let's see. I have seconds, but I'm squaring it. So up top here, I am left with seconds squared times, let's see, meters. And then this second squared, even though we write meters per second like that, really the second squared, since it's in a fraction here, it's down here. So we've got second squared on the bottom too. So second squared cancel. The only unit I'm left with is meters. So that's a good sign that I have done my problem correctly. And so if I want to build a pendulum that has a frequency of 0.714 Hertz, and I'm on Earth, then I need to make the length of this pendulum 0.487 meters. Okay, I hope that is helpful as you kind of work through your example problems on mass spring systems and pendulums and the variables that affect them.